That's you? Did you? Okay. You'll be given the fourth talk. I'm the last one, yeah, the fourth in the session. The last part of the session. Yeah, that's really nice. Okay, good.
I actually was signaling people to come in here about 5 minutes ago, so.
Yeah, but it was a big mess with the coordinator with Julie and that.
Okay.
All right, good morning. My name is Ilko Visser. I'm General Chair for Splash 2016, which will be in Amsterdam next year. And so you should all prepare to come there. But more importantly, I'm now Session Chair for this first OOPSLA session on domain-specific languages. And we have 4 very interesting talks. And the first will be presented by Thibaud. Take it away.
Good morning, everyone. So it's my pleasure to present today our work on synthesizing layout engine from relational constraints. So very briefly, right, program synthesis is going from specification to executable code. The thing is, when the spec grows large, right, synthesis tends to time out. So today I'm presenting an algorithm to scale synthesis to a very large specification by exploiting its structure. This is work done with my advisor, Reuseability, while both of us were at Berkeley. So I want to start by showing an application that our work enables. So what you're seeing here is a user creating a data visualization. So the user is dragging nodes of a tree. And as he does so, the system computes which constraint needs to be added or removed. So the system is actually writing the spec for the user. And such applications are made possible because the constraints, it's not so good. Let me restart. Yeah. So such applications that you just saw are possible because the constraints are relational. So let me explain what I mean by that. So we have here 2 trees that the user could have built, right? The tree on the left. So notice that the difference is the way the nodes are layered. And the trees on the left, the nodes are layers based on the tree height. So that's the distance from a node to its furthest leaf. And that's computed bottom up. On the tree on the right, the nodes are computed based on depth, the distance from a node to the root of the tree. That's computed top down. So the great thing about relational constraints is that you can reuse the same constraints that assigns, that computes the layer for node. And depending on which design the user wants, you're actually the computation is gonna flow differently, right, from left to right or right to left. So as such, relational constraint really bring a reuse. I want to mention here that what we're really doing here, right, this is layout. So what we're really computing is like the position and size of all of the elements that needs to be shown. So the question is, when you write layout with such constraints, how do you actually solve them? So the traditional way, right, is to start with a document that's going to be a tree of nodes. Each of those nodes has attributes or variables such as position, height, and then there are constraints that define their semantics, right? So if you were to solve the layout, compute values for all those variables, the traditional way is to feed them into a constraint solver. So that could be Z3, or that could be Cassowary, a well-known layout-specific solver. The solver then is going to do a search, compute values for all those attributes, and there is your tree. Now the problem is that even for a smallish document, let's say about 1,000 nodes, such solvers are too slow, right? It takes about 1.5 seconds to solve a tree with 1,000 nodes, and that's unsuitable for interactive settings when we do layout to respond to a user action. So we want to give the illusion, at least, that the system provides immediate feedback. Now you're going to tell me, well, when I go on the web and I browse web page, layout's very responsive, so how do the browser do it? Well, the browser uses their own constraint language called CSS that has, its own set of primitives. But a team of experts actually spend a bunch of time writing a constraint solver, a layout engine in this case, very specific to the CSS constraints. So what they wrote is actually a set of tree traversal that can solve any HTML document. And that is fast because unlike Z3 or Cassowary, there is no search, right? Only passes to the tree. So that's great for CSS because we can have fast web page layout. But now CSS is good at some things, but not all things. For instance, one cannot make a tree, or it would be very difficult to draw a tree. So the dream is to enable domain specific layout language, right? Where we can create such language of constraints specific to one type of visualization, like a tree that you have on the left, a tree map, or perhaps in the future CSS, and somehow automatically generate the fast layout engine expressed as tree traversal from the constraints. So now it's going to take a special kind of compiler to go from constraint to this fast layout engine. And that compiler will have to do synthesis, what we call synthesis. So let me give a little bit of background on that. So if you forget the tree, right, if you take your document and you flatten all the constraints and collect them, you end up with a relation such as this one over a bunch of variables. So what synthesis is actually given a set of designated variables that are known, I'll call them inputs. We want to compute a function that will be able to compute all the remaining variables. So here I'm using a hyper-edge notation to denote that function that reads A and B and writes to C. I want to mention that the community has built such tools, such synthesizer. I'll note Confusi and Sketch, for instance. The problem is that, as I hinted in the introduction, is empirically we noticed that such synthesizer scale up to about 100 variables. And our documents are made out of 1,000 nodes on average and have a dozen of variables in each node that needs to be computed. So we have a 2 order of magnitude gap that we need to bridge in terms of scalability. So we're going to do that, and this is what this talk is about, by doing what we call modular synthesis. So we're going to take our big relation and then break it down into smaller relation, actually around conjunction. So here I can create 2 smaller relations, red and green. That's what we call the decomposition step. Then I'll apply actually a local synthesis tool, so that could be Confusi or Sketch, to generate function for each of these smaller relations, right? And the final step really will be to come up with a way to actually compose the result into a bigger function that solves the overall relation. Now the key difficulty is that, even if I know the overall input, the input of the blue relation, I don't know the input at the local or decomposed level. I don't know the inputs at the level of the red or the green relation. For instance, here we have E and F that are like connection variable that are used to pass value from a function of the red relation to that of the green. It could have been the other way around. So I'm going to present today a way to a modular synthesis algorithm that works on tree structure relation. So the fact that it's a tree, it's a restriction, but at the same time, it actually enables us to generalize the technique to grammars of tree. That means we can synthesize an engine not only for a single document, but for many documents, right? All of those generated by a tree grammar. We build upon previous work from the program synthesis community. In fact, we rely on tools that the community produce for local synthesis. And I want to mention that our work has connection with constraint planning and also mode inference of logic program. And for the last connection, you can see it when we need to infer inputs at the local level. That's actually similar to inferring mode of a Prolog-like program. So let's dive into an example. So we're gonna synthesize a fast layout engine for this simple document here, made out of two blocks, A and B, and you can see the constraint defining the two blocks down there. So they're all equation, they're relational constraints. Now what we want to do is come up with a set of assignments computing those values. Once I have those assignments, I can actually schedule them into a set of tree passes using what we call an attribute grammar scheduler. And using work from others in our group, like Leo's, you can actually make those traversal parallel or even incremental. Now, that's the case when we work on a document. As I hinted, our algorithm work on grammar. So what we do is we actually go from a relational attribute grammar to a functional attribute grammar. So how do we do it? So first step is decomposition. So I start with my document made out of two nodes, and I'll actually break them down at the node boundaries to create what I call block, which are just named sets of constraints. So I end up with two blocks. Now I'm not going to stop here. I'm going to keep decomposing the constraint around conjunction to create as many blocks as I can. So I can make these 4 blocks here. Notice that I could have made more block, right? Since I'm going to consider all subsets of constraints. But for the purpose of this example, I'm going to assume that I have an oracle that tells me I just need the 4 I have in the middle of the slide. Once we have decomposed blocks, we're going to apply a local synthesis procedure to create function. So that could be your favorite synthesis tool. So for instance, so that means that we actually have to choose which variable are going to be input and output. So I have no way to know which one I need beforehand. So I'm going to consider all possible partition of variable into input-output sets. So for instance, for the block A1, we can generate 2 functions, one assigning x from I and the other assigning I from x. So for the final step, I'm going to collect all the functions I've generated. And these now become my candidate function. And I'll have to somehow stitch them together to create a bigger function, the layout engine, that solves the document, that computes the layout. To do that, I'm going to create a hypergraph of candidate function. So that's a graph that shows actually all the possible stitching we can do. Right? Each path is a different composition of the function. The key thing to notice here is that we don't actually need to use them all, right? In fact, you can see some functions are inverse of each other, so it would be silly to use both of them. So what we need to do is come up with a sufficient subset of function. And we want a subset such that the dependency of all the chosen functions are met. So that means that their inputs is available, so the variable they read are computed before the variable they compute. Inputs are available before output. We want no cycle, because those represent impossible executions. And we need also to make sure that we select n of function for all variable to be computed. So these are the 3 key criteria. Now for this example, it's enough to select these 4 functions here. And by composing them with each other, I get a bigger function, my layout engine. The really nice thing is that I can express my 3 correctness criteria you have at the bottom of the screen as graph properties, right? So the chosen 4 function are actually an acyclic hyperpath that spans the whole graph, an acyclic spanning hyperpath, if you want. So now we know what we need to compute. The question is, how do we compute it? Well, that's sort of where you have to go in the paper to get all the details. But in a nutshell, to find an acyclic spanning hyperpath in a hypertree, that's an NP-complete problem. So we can reduce it to an SMT constraint. We can encode it as an SMT constraint, feed that into Z3, right? And the key insight here is that the SMT encoding is actually going to infer mode for all the variable. Now, there is one thing I won't really talk about in details, and that's how we generalize to grammar. So again, in a nutshell, you can think of a grammar as just a document, right? A tree that has cycle. The cycle represents recursion. So what we need to do is the solution, the layout engine, will also have some cycle. So we need to be careful to allow cycle that actually represent an inductive proof, but not those that represent an impossible execution. So that concludes the technical part. So I just want to do a brief summary of our evaluation. So we evaluated our work along 2 axes. The first one was how fast our layout engine compared to a general purpose constraint solver. So I was measuring the time in the dotted box you see here. And we also looked at how our layout engine scales with document size. So we did 3 case studies, and you see them on the left. And here I want to mention that our synthesized layout engine are actually in JavaScript. So that means we can ship them with any web page, and again, they can be used to render documents in any browser. The 3 pictures you see here are actually rendered using our synthesized layout engine. So we have a case. The first case study is guillotines, which is a simple layout system dividing the screen vertically and horizontally. Then we have a tree data visualization, and finally a tree map data visualization. So when we compare the speed to the synthesized engine with respect to Z3, we see that we are about 1.5 to 2 orders of magnitude faster, right? And that's, one of the reasons we believe that we're so much faster is because we do no search, right? We only do passes on the tree. So you can see that the first case study is compiled or synthesized down to a single tree traversal, whereas the tree map, our most complex one, compiles down to 5 tree traversals. Now, if we look at how the engine fares as the document size grows, we see that we scale linearly. And again, that's expected because our engine are a bounded set of tree traversal. So when you read the plot, just they're log, so be careful. And the one more thing I want to point out is that Z3 actually answer unknown on the 2 largest document for the last 2 case studies, and that's because those data visualization contain nonlinear constraints. And if you put too many of them, then Z3 just gives up. So that concludes my talk. So I've presented a modular synthesis technique working not only on trees but on grammar of trees, right? You take a big relation, you decompose it around conjunction, you apply your favorite synthesizer, and then we stitch the result for you. The vision for this work was to enable domain-specific layout language, create your own language of constraints, compile a layout engine as JavaScript, ship it with any web page, so it's easy to deploy. And even though we applied our algorithm to layout, I want to mention that there is nothing layout specific in it. We just need a tree structured relation. So, for instance, it could perhaps be applied for our hardware description language when you have modules and a tree of modules with timing constraints. And could perhaps also work for some type checking algorithm where you have constraints over an AST. That's it.
we do have time for questions. If you have a question, please come up to the microphone.